Hello, my name is Tom Klepper, and welcome to Part 3 of the Basic Electrical Circuits class taught at the Route 9 Library and Innovation Center. This part is called Sensors and Arduino, was taught on October 15th, last Tuesday, and based on some of the feedback I got from the class, I added a slide and I rearranged a little of the content to hopefully make it a little clearer. So we're going to start off this class by talking about sensors and the Arduino and doing an overview, again refreshing people's memory of what the Arduino is all about, and then move right into sensors and transducers. We're going to focus on a handful of the most popular transducers or sensors that one would want to incorporate into your project. The first one is the diode, or particularly the light emitting diode. Next, move on to the photoresistor or photocell. Next, what is capacitance, followed by a servo motor. How would you measure temperature? And then finally, some kind of contact closure or push button input. So the Arduino microcontroller board, we're going to interface these to what we're calling sensors. So I have two different kind of terminologies to go over. We're calling a sensor is kind of any device that takes a response as an input to the microcontroller, and a transducer is a more generic term about a device that will convert one form of energy to another. So for instance, if you convert electrical energy to optical energy, might be a light bulb, or let's say electrical energy to acoustical energy might be a speaker. So again, if you want to learn more about Arduinos, go to this website. They have everything you need to know. But I want to take note to a couple of places on the Arduino itself. This is where you actually access the input and output pins. So anything you're going to input to the Arduino will go into these spots, and outputs will come from them as well. A couple other pins to notice: we have a plus 5-volt source here from the Arduino and grounds there, and we'll talk about what they are next. But the Arduino can actually help source your sensors if they do need power. So to refresh our memory, what we're trying to do is make some kind of a project or a game. This is the example of a little game I put together to introduce the class. It's the Route 9 Library Wire game, where you take this little loop and you try to trace it around the R, the T, and the 9 without touching it, and make it to the very end, kind of like the old game, the operations game. So we have at the heart of it an Arduino Uno, which is a fairly inexpensive board. We have some LED transducers. Again, they convert electrical energy to light. Here, 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 and there. And again, most projects are probably going to have some kind of LED to them. And we have a speaker transducer incorporated as well. And then finally, this part where the loop will touch the metal part of the wire is actually an electrical contact sensor, like a push button. So something to note about the difference between our simple circuits and the Arduino: if you remember from our classes before, we always had a voltage source, most likely a battery, had a positive and a negative polarity to it, that we'll call V sub S or V source. And also, of course, it would have a current flowing through it and a resistor. For the Arduino, what we're going to have is the output of the Arduino pin is now going to be the positive part of our voltage source. And then the ground part of the Arduino is going to be the negative part of the voltage source. It's still V sub S, where the positive and the negative, but it's going to be sourced by the Arduino itself instead of a battery. So in some respects, this Arduino is going to look like a battery. Now, something we've added to this little schematic are these little symbols for ground. And all these mean is that essentially wherever you see a signal like this ground terminal or pin, they're connected together virtually. But in reality, they are connected together. But they're not shown that way in the schematic, just to make it easier, because you could have a lot of these ground, terminals shown anywhere in your schematic. So just whenever you see this on the schematic, just know that the grounds are all connected together. So I want to kind of show you plotting Ohm's law when we move into the diode. I think this might help to explain when I talk about what a diode is. We'll look at what a resistor is. So here is our simple circuit. We have a voltage source, current flowing through it, and a resistor. If we plot this, if we plot the current flowing through this, we get these straight lines. And again, remember, I equals V over R from Ohm's law. So what this is telling you is, if we put a positive 1-volt source here, battery, current's going to flow from the positive to the negative through the resistor. the resistor is going to limit the current based off of Ohm's law. So put a 1 volt signal or 1 volt battery across the resistor, we're going to get 10 milliamps for a 100 ohm resistor. Now, if we change this to a 200 ohm resistor, we would have to put 2 volts across that resistor to get 10 milliamps of current. If we had a 400 ohm resistor, we would have to have 4 volts. And again, as you would expect, it scales because this is linear. They're straight lines. And the slope of this line is determined by the actual resistance. So that in this case, if we're looking at a current on this axis and voltage on this axis, the steeper the slope, the lower the resistance. So a little note about polarity, I mentioned that before. So in this topology, we're talking about a positive polarity. This is where, by convention, the current flows from the positive part of the battery through the resistor to the negative part. And that's shown on this part. We call it positive voltage. However, you notice this graph has a negative voltage. So we're going to call that the negative polarity. And all we're saying here is, if you keep the same convention as current flowing in this kind of clockwise direction, if we swap the terminals of the battery, just kind of pick it up and turn it around, essentially what we're saying is, hey, we're putting in a negative voltage. So there's no such thing as negative voltage. All it's saying is, oh, that's the polarity of it. So if you take this battery and you switch it around, put it in the circuit this way, and we say, oh, current's supposed to flow through this, you go, no, actually, the current's actually flowing through this, so it's going to yield a negative current. So this negative voltage yields this negative current. Again, there's no such thing other than just the polarity. So when you plot it this way, you show that it's still a straight line, goes through zero, right? Zero voltage will yield zero current in milliamps. But it just kind of shows you that if you flip the polarity around, it still continues to be a resistor. The only difference is that you're getting this supposed negative current. So I wanted to show you, this is how we kind of plot a resistance based off of Ohm's law. So now we're going to move on to something called a diode, and I call a diode a current check valve, and you'll see why. If we plot the resistance that we've seen before, you get this straight line, meaning that, you know, for a certain voltage, you come up here, you'll get a certain positive current, or for a certain negative voltage, meaning the opposite polarity, you get this negative current. It's still a straight line. If you look at this is called an IV curve, the current versus voltage curve. If you look at that, a diode in this forward polarity kind of looks like a resistor, but it's very nonlinear. You know, so it starts off kind of slow, and as voltage increases, the current increases very rapidly. However, if you look at the negative voltage or negative polarity, no current flows through. So it's just saying, if in positive polarity, the current will flow through the diode. And matter of fact, it flows through very quickly as the voltage goes up. But if you take the voltage and pick it up and turn it around, you change the polarity, no current flows through. It's almost like a current check valve. What it looks like schematically is this. You have this little arrow with this line. That's the diode symbol. This part of the diode is called the anode or the positive. This part's the cathode or the negative. So current always flows from anode to cathode. It flows in the direction that this symbol shows, like this. This is our conventional current flow through a diode. So what this means is that in this direction, in this topology, this is the forward or positive polarity. So the current will flow through this diode, and you're in this region here. If I flip the diode around, or I change, let's say, whatever stimulus is out here, but let's say I flip the diode around so I'm at negative polarity, no current will flow through. So it's important to know which way the diode is inserted into your circuit to see, will current flow through in this direction and will not flow through in the other direction. Now, why would you care about that? Well, in this situation, in the Arduino, there is actually a diode, and a physical diode. Here is the DC power input. It's a you can get a power plug, you plug it in here, and you notice that the center pin for the plug goes along this trace, goes through this diode and on to the power supply part of the circuit board. You see this little stripe here on the diode. That stripe indicates the cathode. So you know that current will flow through this diode and into the power supply. So why is it there? Well, the reason it's there, it's simply for protection. If for some reason somebody puts in a power supply that fits in there, but it's got the wrong polarity, this diode protects your circuit from being damaged. So it's used as a protection device. So that's what that diode's there for. It's literally used as a current check valve. course, there's another reason or another place we use diodes in the light emitting diodes or LEDs. And again, we've heard of these. Our houses are now filled with LED lights. And the reason why we care light emitting diode is it needs to go into the circuit a certain way. So here's the LED symbol. And again, it is a diode, but it's got two little arrows coming out of it. What that means is it's a diode where light comes out of the diode. That's what these little arrows mean. Here's the anode and here's the cathode. What this is telling you is that if current flows through the diode of a sufficient amount, you will get light coming out of the diode. Now, just they do have diodes that sense light, and the little arrows go in. They're called, they're basically light detecting diodes, photodiodes. So here is a picture of an actual LED. One of the couple of nice things if you're trying to figure out the polarity is typically out of the package, the longer lead of this particular package is the anode, is the plus, and the shorter is the minus. So already you know how to hook it up. Or the cathode usually has a small flat spot on it. So if you take it out, you already know, oh, the current has to flow into the long lead and out of the short lead. But if somebody has to cut the leads off, you can see by this flat spot. And again, what this means is that if you have current flow through here, let's say of about 10 milliamps, you'll get lots of light coming out of here. If you happen to put the LED in backwards, it's not going to hurt the circuit, but this thing's not going to light because we know current can't flow in the opposite direction. So that's why it's important to know about what a diode is, because if you put your light emitting diode into the circuit wrong, it just simply won't work. So let's go to our schematic here, and this kind of culminates the last few classes, Ohm's law, components into what you may want to do. So here we have a couple of pins from the output of the Arduino. So we have our ground pin of the Arduino, and we have an output pin. And we're going to have some voltage out, V. Now for Arduinos, the voltage out is typically 5 volts. In our previous experiments, we've been using 3 volt, two AA batteries. So we have a V out, we have a V1 across the R1, so there's a voltage drop across here. We have a voltage across the LED, and of course we have a current going through this circuit. So we can use Ohm's law to figure out what's going on. We can say, oh, we have a voltage out here, a voltage drop across V1. We know the voltage drop is because we have a current going through R1 that creates that voltage drop. And then finally, it'll create a voltage across the LED we call VLED. Now we know, see these two grounds are here? We know that they are connected together to make our complete circuit. So the current flows through here, through the LED, back through the grounds and into the Arduino pin. And again, all you need to do is assume that this is just like a battery. So let's look at the equation of Ohm's law. R1 equals V1 over I. So the voltage drop across R1 divided by the current going through would equal R1. That's V out minus VLED. The voltage drop from V out to VLED will be V1 divided by I. So what do we know? We know that V1 is 5 volts. V out is 5 volts. For right now, we're going to assume that the VLED is 1.9 volts, and I'll explain that later, but just trust me on this. We're going to assume that the voltage drop across the LED is a fixed 1.9 volts. So we have 5 minus 1.9. Now you go, okay, I want 10 milliamps to go through my LED. Now, as it turns out, the LED, that light that comes out of the LED, is proportional to the current flowing through it. So you just have to kind of know that, oh, let me start off with just about 10 milliamps and see how bright that is. So 5 minus 1.9 all over 10 milliamps gives you 310 ohms. So essentially, when trying to drive this LED from an Arduino, you need about a 300 ohm resistor here to get the proper amount of current, 10 milliamps, to go through the LED to give you the correct amount of light. So this is how we've learned about, voltage, voltage drop, current, Ohm's law, what a diode is, and we've used Ohm's law to figure out what resistor we need to limit the current through the LED. A little note, again, we're saying that V out is plus 5 volts. Now, when we go to actually do the software, we're going to tell the Arduino, make that pin a digital 1. And when it does that, it's going to turn that on to 5 volts. It's going to make this V out 5 volts. If we tell the Arduino, no, make it a digital 0, which is turning it off, it literally makes that 0 volts, which will effectively shut off the LED because no current can flow through here if this is 0 volts. You just look at, you can just look at the Ohm's law, and if this is 0, no current can flow through here. So the first little experiment we're going to look at is LED polarity. So we're going to use the meter to read the voltage drop across the LED for a very, very small current. So what we're going to do is going to grab our multimeter. We're going to select this setting here. This is called the diode or continuity selection. And what it does is it literally puts a very small current from the red terminal through whatever it's measuring. Could be a resistor, could be just contacts, an LED, a diode back into the black terminal. Now, if you just connect these together, which is a good idea, when you get this set up and you select this setting, just connect the two leads together. This should read 0, or it'll actually beep. So see, this little gives you an audible signal that it's measuring 0 resistance across this, or the voltage drop across this is 0, because again, it's inducing a small current and measuring the voltage drop across this. So it should equal 0 and it should beep. However, when you put the LED across here, where the anode is at the red and the cathode's at the minus, where this little amount of current, it's like a milliamp or less, flows through here, it'll show you what the forward voltage drop is in millivolts. So if the drop across this, I'm arguing, is about 1.9 volts, then you should see something like 1900 here, as in 1900 millivolts. What you'll actually see is probably something less because it's a much smaller voltage. So you may see 1200, maybe 1500, which would be 1.2 or 1.5 volts. But essentially it's showing you the voltage drop across this. Now, go ahead and take the LED and put it into this backwards. When you do that, we noticed before that no current can flow in the opposite direction, so you should see 0 here. So that's how you can use a multimeter to check, not only check your LED, but also check the polarity of it, make sure it's working right, and you can put it into the circuit correctly. So here's the second experiment, and this is kind of interesting. So again, we assumed that the voltage drop across our LED is 1.9 volts approximately. So what I want you to do, we're going to calculate R1, this current limiting resistor, for a current of 2 milliamps, 9 milliamps, and 16 milliamps through our LED. Remember before I said let's pick 10, so let's go ahead and design it around 2, 9, and 16 milliamps. So here's our schematic. We have voltage source V sub S. We're going back to our 2 AA batteries. R1 we're going to calculate. We're going to have a certain current going through the LED, and we have V LED. So we use this formula to calculate the resistance. And then here's the table you get. So for 2 milliamps, 9 milliamps, and 16 milliamps, we're going to assume that the VLED is 1.9 volts. You calculate the following resistances. So for 2 milliamps, you get 550 ohms, 9 milliamps, 122 ohms, and 16 milliamps, only 69 ohms for this R1. However, I mentioned before that when you go to actually look up resistor values, they only come in certain discrete values. And so what you do is you pick the nearest one. So you look at this and go 69, oh, there's a 68, that's pretty close. 122, well, there's 120, that's pretty close. And for 550, there's a 560, and that's pretty close. So we'll use 68, 560, and 120 for our resistors. So what I want you to do is go ahead and hook up this circuit with the 3-volt battery, put in the resistor that you have. Now, in the class, I gave out bags that had these specific values, 68, 560, and 120. So pick one or do all 3 of them then. And then what I want you to do is do 2 things. When you go to hook up the resistor and you hook up your LED, I want you to, 1, notice how bright the LED is. Okay? And then the second thing I want you to do is measure the voltage drop, the actual voltage drop across the LED. So if you fast forward and you guys have done the experiment, I'll kind of tell you how it turns out. You'll notice that the 2 milliamp one, the LED does light, but it's very dim. You also know that the voltage drop across this is probably somewhere between 1.8 to 2 volts. I forget which one it is. And then the 16 milliamp, when you do it will be very, very bright. And again, you'll notice that the voltage drop across there is pretty close to 1.9 volts. And you'll see the 9 milliamp is just about right. It's like the old, the 3 bears, and The porridge is too cold and too hot and just right. So that's kind of why you can see visually by doing this experiment why I choose about 10 milliamps, because it gives you enough brightness and still it's not a lot of current. But you can also see over this incredibly wide range of currents from 2 to 16 milliamps why I choose 1.9 volts, because it's right about in the middle. So it's a good way to just start with 1.9 volts. Go ahead and do it. If you need to adjust it, you can, but it's usually close enough. So this is how you calculate the resistance value for an LED. So let's move on to the photoresistor or photocell. So a photocell changes its resistance with incoming light. So this is what it physically looks like. There's one in the bag that I think I handed out at class. And here's the symbol. It's got a little resistor with a circle around it, and then the arrows are going in. Remember, in this case, the arrows are going in because this particular sensor is sensitive to light. So this shows you, oh, this has a light input to this sensor. So for this third experiment, what I want you to do is go ahead and take your multimeter, select the ohms region. Now, for this particular photocell, I've chosen one that should vary somewhere between 2 kilo ohms and 20 kilo ohms. So 20 kilo ohm range might be a little pushing, so just jump it up to 200 kilo ohms to make sure you're covering it. And what I want you to do is connect it to the multimeter. It's just a resistor, so it has no polarity. You're just hooking it up like a resistor. Maybe select the 200 kilo ohm resistor, and then point the thing at the light and notice what resistance you get, and then cover it up with your hand and notice the resistance. So you can see how much light it takes to change this resistor, and you get a fair amount of change of resistance with this photocell. More than an order of magnitude, which is really impressive. So here we have a resistor that changes resistance with incoming light. And obviously you could use this for all kinds of applications, like, oh, did somebody turn on the light? Or a great one if you're making a night light. You use a little photocell, and you can tell when the light gets down a certain amount, or maybe turn on an LED to help you illuminate the hallway or something like that. So a lot of applications can use this photocell or photoresistor. The next thing is called capacitance we're going to talk about. So I'm going to do this a little different. I'm going to basically kind of go, oh, here's the symbol of capacitor, here's what it is, and then we're going to talk about, well, what is capacitance, and then kind of end up with, oh, what would you do with it? So a little bit backwards, but just kind of bear with me. So capacitance. So here we go back to our little simple circuit. We have a voltage source, a switch, a resistor, and a capacitor. So here's the symbol for a capacitor, two parallel lines. Here's what it actually is. So if you take a capacitor and kind of could really look at it and kind of destruct it, you would see that there are two metal plates of a fair amount of area, and it's separated by an insulative material, and it's connected into the circuit like this. So simply its capacitance is equal to this area of the two electrodes, right, times some constant divided by the thickness between the electrodes. So you can tell that if I need a capacitance of a large amount or large value, I need to either increase the area of the capacitance or decrease its thickness. Now, for actual, let's say, film capacitors, this thickness can be in the order of microns, micrometers, and this area can be, tens of feet. I mean, these can be very, very large area and very, very thin if you want capacitance of a large amount. And remember, we talked about capacitance is measured in farads. Here are some capacitors, and typical capacitance there's one that's 10 microfarads. We go back to our prefixes. This is 1,000 microfarads. This one is 10 with 4 zeros, so 10 times 4 zeros, picofarads, or 10,000 picofarads. This one is 22 with 2 zeros, so that's 2,200 picofarads, which would be 2.2 nanofarads, or 0.0022 microfarads. So obviously capacitance, when you go to actually buy one, are pretty small values, hence why we need to look at using those prefixes of like micro and nano and pico, etc. So these are small values. So that's what a capacitor is. That's the symbol for it. This is how you would calculate what its capacitance is. So what is it? Well, let's go back to our example. Oh, I'm sorry. Let's go on to talk about what some capacitive sensors are. So a capacitive sensor might be a humidity sensor, which changes its capacitance as a function of humidity. They have proximity sensors, which essentially this little transducer, as it gets closer to a target, usually a metal target, will change its capacitance as it gets closer. And there's I don't know if you remember from Star Trek, there was a thing called a theremin, that between this electrode and this electrode, if you put your arms in, your body actually changes the capacitance, and it's a transducer. It changes capacitance to a sound, and that's what the intro to Star Trek was, using a theremin. So these are some capacitive sensors. This is a popular one, humidity sensor as a capacitive sensor. So, okay, what is capacitance? So now I'm going to go back to the hallway example, where we're taking this hallway into the doors into an auditorium. So let's take note that this hallway and the auditorium has people milling about. Remember here, just like the electrons, there are kind of people milling about the hallway, and in the auditorium, maybe these are the ushers getting ready to seat people, and these are guys who are just hanging around getting ready to go into the concert. So I kind of threw a couple people in there to show that yes, there are people still in here, but not that many, let's say. Also note that they're going into the auditorium, but they're not leaving the auditorium. They're just filling it up. Okay, so the minute we open up the doors to the hallway, people start going into the auditorium. So remember in this example before, we were measuring the flow of people through the hallway by somebody standing here with, let's say, a little counter. And every time somebody went by, they counted 1, 2, 3, and you could actually accumulate or count the number of people that passed by this spot per second would be equivalent to the current, just like the number of electrons that flowed through a wire in a given second was the equivalent to the current. So we open up the doors, people start moving into the auditorium, and as time goes in, more and more people flow in. So we actually get current flow, if you will, or people flowing through the hallway, filling up this auditorium. So we're getting real current flow, if you will, of people, just like we would get electrons in the wire, but people are flowing through the hallway into the auditorium. As time goes on, the auditorium fills up more and more until finally the auditorium is full. Everyone's in their seats. There's no more seats available. And as soon as that happens, people stop flowing into the hallway, right? Because they can't go. So they may still be milling around here and talking, etc., but there's no net flow of people, right? Because they've stopped moving this direction. They're just kind of milling about. So, from the minute we open up the doors, you get the flow of people into the auditorium until it fills up. And this is essentially the same as the capacitance. So let me see the next. Yeah, I'm going to go back. I'm going to go back to this one because I just want to show you that. So when we flip this switch on, so we have this voltage source, and again, there's electrons all in this wire and all in the plates of the capacitor. So we flip the switch. The minute we do this, electrons can flow through. They're limited by the current, the resistor, and they start filling up into the capacitor. Again, there's already electrons in here, but they get a higher density of electrons. So current flows through this, into this resistor, into the capacitor, the minute we close that. Now, as soon as this capacitor is full of these excess or these extra electrons, the current stops flowing. So essentially, even though the switch is closed, the current can't flow through here. And again, there is no contact. This electrode and this electrode are separated by this insulator. So no electrons are actually flowing across here. Just like if this was an auditorium, people would go into the auditorium, but they're not leaving the auditorium. They're not going out the exits. They're going into the auditorium, but they're once it's full, it's stopped. Again, so there's no actual current going across this junction insulator. However, the minute you switch this, electrons flow into here because this capacitor actually accumulates charge. That's what it does. It stores charge. It stores electrons. So and as soon as it happens, you charge up this capacitor and it's full. So theoretically, you could charge up this capacitor, take this capacitor out of the circuit, and you could measure a voltage across that capacitor, meaning that there is stored charge on that capacitor. It'd be like, oh, the auditorium's full of people. And just like if you were to, discharge it, if you will, you could have people leaving the capacitor, electrons leaving the capacitor, like people leave the auditorium. So I just wanted to show you that is how the capacitor actually works. You turn on the switch, it stores electrons, stores charge, and the opposite is true. So let me go back to this graph here and show, here's the circuit. And then here we have a voltage source. It's a little bit different. I'll describe it, but it's going through this current limiting resistor into its capacitor and back all the way to our voltage source. Now this voltage source is what we call a pulse. It's very simply that voltage source is going to be 0 for the first 0.1 second. So here we have a graph of time, every tenth of a second up to 1 second. And then here we have on this y-axis voltage, and this is the actual voltage that we're either going to be across our source or across our capacitor. So what we have here is this blue line is 0 for 0.1 seconds, then this source goes to 5 volts, and it stays 5 volts for a half a second, and then it goes down to 0 volts, right? So for 0 to 0.1 seconds, it goes, then this source goes to 5 volts here. This is the voltage across V1, or V sub S. Goes up here for half a second, so from 0.1 to 0.6 seconds, it's going to stay at 5 volts, and then this voltage is going to go to 0. It's going to shut off and go to 0, okay? And then this red line here is the voltage across capacitor. So if you're going to measure this voltage, this is the red line. So here's what we actually have. So the voltage across the source is 0. It steps up to 5 volts. However, the voltage across capacitor is slowly charging. So this is just like the hallway doors have opened to the auditorium. People are flowing in. They're finding their seats. They're flowing in. They first flow in pretty quickly, and then milling about trying to find those last couple of seats, and the usher's trying to, oh, could you move and stuff. And all of a sudden, finally, the auditorium's full. So now the voltage across the capacitor is the same as the voltage across our source. But you see there's a delay here. It takes time for that capacitor to actually charge up and fill up with electrons, right? And then here, if you turn off the voltage, this is just like, all right, the show's over, the auditorium doors open, and people start shuttling out. And they come out pretty quickly. They're getting out of the auditorium. They have to go to the cars. All of a sudden, you got these stragglers. They're watching the credits. It's a Marvel movie, and all of a sudden, all right, so now the Marvel credits are over, and finally everybody has left the auditorium. But there's a discharge time that takes for this to happen. It does not happen instantly. If this was a resistor, let's say, so these two were resistors, and we would look at the voltage across this, the voltage across the resistor would go instantly to 5 volts. And when it shut off, it would go instantly to 0, because there is no charging or discharging of a resistor. It's only this capacitor that has this ability to store charge and discharge. So kind of go over this again. The source goes from 0 to 5 volts. The capacitor charges up. And when we look at the voltage across the capacitor, it takes about this long before it's finally charged. And then, oh, we're going to discharge it. It takes a while for it to discharge. So this time constant is what we're going to actually utilize. And when I say time constant, it's actually 2.2 times this current limiting resistor times the capacitance. So in this example, R1 is 100 kilo ohms. C1 is 1 microfarad, which means it's 0.22 seconds. So what we're actually saying is the rise time, or this time constant, is they call the 10 to 90% rise time constant. And what that means is at 10% of the final voltage value being 5, 10% of that being 0.5, at the point when the voltage across the capacitor hits 10% or 0.5 volts, so start a stopwatch. So you're going along, all of a sudden it hits to 10%, you start the stopwatch, you wait for 0.22 seconds, and then you should hit the 90%, which is 90% of the final value of 5 volts should be 4.5 volts. So after 0.22 seconds, you should hit 4.5 volts, and you can see you actually do. So you can see the reverse would be true here. So this would be the 90-10 fall time, not rise time. So when it hits 4.5 volts, you start the stopwatch, and then when it finally hits 0.5 volts, you stop the stopwatch. That distance in time, that delta time it took for it to either charge or discharge, is called the time constant, and you use this value to calculate it. This simple relationship. So what does that mean? Well, what this means is two pretty cool things. Let's go to here. Let's say, for instance, we're going to take this resistor and we're going to change it from 100 kilo ohms to 10 kilo ohms, right? We're going to decrease it by a factor of 10. Or let's say so maybe this is a photocell that goes from being 100 kilo ohms to 10 kilo ohms. Or let's say you hold this constant, it's a fixed resistor, and let's say it's one of those capacitive sensors like a humidity sensor, and you take it from 1 microfarad to zero point 0.1 microfarad. So let's say it's some a proximity sensor or something where its capacitance changes from 1 to zero point 0.1 microfarad. Either way, what we're saying is we're going to change this time constant by a factor of 10. So instead of 0.22 seconds, we're going to change it to 0.022 seconds. So we're either decreasing, doesn't matter which one you do, we're decreasing the resistance by a factor of 10 or the capacitance by a factor of 10. Now look at our scenario. So the blue is the voltage source waveform. The red is the voltage across the capacitor. Now look at it. Now it rises up really quickly, right? So it takes no time to fill up the auditorium. So this would be the same thing as saying the difference between a big auditorium before and let's say a little 20-seat auditorium. So a 20-seat auditorium fills up really quickly, whereas a big auditorium takes a longer amount of time like before. So this would be a big auditorium. So a big auditorium has a lot of capacity to hold people, whereas a small auditorium has very small capacity to hold people, just like its capacitance. That's kind of where it came from. So you can see that we've decreased our sensor or device by a factor of 10, and we've changed its rise time. So you can kind of see here our 10 to 90 rise time is much smaller. It's 0.022 seconds. So what this is saying is, depending on the sensor, if this was an Arduino pin, let's say, so now instead of this voltage source, this is an Arduino pin, and I hang a resistor and a capacitive sensor off of it. If the Arduino is able to measure this time constant, which by the way, a few lines of code you can actually do, so an Arduino can measure this time constant directly. From the change of time constant, I can tell you that either R1 or C1 has changed. So I can use this very simple circuit to measure the change of a changing resistor like a photocell or a changing capacitance like a humidity sensor. So this is where we would use kind of like, I wanted to introduce capacitance because it's used in this time constant kind of circuit to measure changing resistance or changing capacitance, and this is how you do it. So this is just a very quick overview of this. We can certainly go into this in more detail later. Next is the hobby servo motor. So this is kind of cool. This is a little prepackaged device. They only cost a couple of bucks. Inside of it is a DC motor, a bunch of gears, and this this kind of winged thing here. There's a potentiometer to feed back to a control circuit. Essentially what you do is you supply this hobby motor with plus 5 volts, ground, and a signal line. Depending on what you supply the signal line, this thing will change from plus 90 to minus 90 degrees. So you can use this to impart some simple motion to a project. You know, let's say you wanted to have a little figurine kind of move around a little bit. You could use the hobby servo motor. They have some of these that are continuous. You could actually make your own little clock. But it's a very simple way to impart movement into your project. And it's very simple. You take the signal pin and you just connect it to one of the output pins of the Arduino. And if you only have one hobby motor, you can have the red line go to plus 5 volts and the black line go to ground. Now keep in mind that if you plug an external source in here, this part of the power supply, which is kind of right here, actually it's right here, can only supply about 800 milliamps. These hobby motors only take nominally a few hundred milliamps, but if you stall them, they can take over an amp. So you got to be a bit careful. If you do have that worry, or you have multiple hobby servo motors that you want to control off of this, you'll need to make sure that you have an external power supply. That's all. So you would have an external 5-volt supply to power these guys, but you could still control them from the Arduino. That doesn't take much current. So there you go. That's you know, if you want to have a little motion imparted into your project, and you just buy a hobby motor and connect it to Arduino, and you're off and running and it just takes a little bit of code to make that happen. It's kind of neat. Along that same vein, if you wanted to measure temperature, you would take your Arduino and you would hook up, here's a particular device. It's called an MCP 9801, and you connect +5 and ground to it. And this uses something called an I2C protocol, but it just takes two particular lines. It's A4 and A5 on the Arduino Uno is the I2C bus. You may need a couple of resistors from here to +5, some like 4.7 kilo ohm resistors. I didn't put them in for just sake of clarity. But simply, this thing measures temperature and a lot more. It's called, what I call it, the single chip sensor solution, meaning that I can get temperature out of this single chip, and all I got to do is hook up the lines. I don't have to have basically any other components. You can get obviously temperature sensors this way, acceleration, pressure, clock, and even more EEPROM memory. So you can get a bunch of sensors that are called single chip solution. You literally just hook them up to this I2C bus, and there's an I2C library that you just call, and you can have multiple ones on this line. So this is kind of like a bus. So I can hang a bunch of these sensors off of the same SDA and S-clock line. Finally, we have the contact closure or push button digital input to the Arduino. So we go back to our Arduino, and now we're going to define one of these pins instead of output pins like we did for the for the hobby servo or driving an LED. We're going to make it an input pin, and we're going to configure it like this. So essentially what we have here is, if I mentioned that this Arduino pin either goes from +5 to 0 volts, right? Now in this case what we're having is it's acting like an input pin. So when this push button is open and I say, what's the voltage at that pin? I could go over here and go, okay, I'm tracing the line. Well, that's an open circuit. Okay, this goes up to +5 volts. All right. So the voltage, there's very, very little current going through here. So the voltage on here is pretty close to 5 volts. Now, if I push that button in and I ground that, so I'm attaching the ground. Again, remember, these are connected together. I'm attaching the ground right to that point. Well, then we know that the voltage across there is 0. If you wonder what's that pull-up resistor for, it's pretty simple. If you say, if this push button is out, so it's not connected, and you say, oh, okay, it's 5 volts. If I put the push button in and short that out, if that resistor was not there, it would short the +5 volt to ground, and you'd short out your power supply. So you need that pull-up resistor to isolate that. When you short this out, you're going to get maybe 1/10 of a milliamp to flow through here, which is not a big deal. But you need to isolate it so you don't short out your supply. But you also kind of need it to make that thing defined as 5 volts. Define that pin as 5 volts. Now, as a kind of a disclosure, some of the Arduino pins, if not all, have internal pull-up resistors. Okay. Now, I just did this to show completeness. And maybe in sometimes best practice, it's best to put an external pull-up resistor. But essentially, this is how you would wire it up. This goes to +5 through a 5 to 10 kilo resistor, and this is your ground. So in the wire example of the wire game, you literally have ground goes to the loop, and the root 9 part of the wire is this part. So that's literally, if you were to see how it's hooked up inside of it, it's just hooked up as a push button. And the minute this loop connects to any part of the wire, it feeds back the Arduino that, oh, it's shorted out, they've touched the loop to the wire, and one of the LEDs goes off. So this is what they call the push button or momentary contact inputs. And essentially what you're doing is you're changing the input, again, from +5 or a 1 to ground or a 0. So when you go to, in the software, you go to read that, you say, hey, what's the status of that pin? If that status comes back as a 1, you know that this is connected to +5 and this push button is not connected. If it comes back as a 0, that means, oh, it's grounded, or this push button is connected. So you can query the status of this pin to find out, is this push button pushed or not, just based off of if this is a 5 volt or a ground or a 1 or a 0. So one of the things you got to watch out for in push buttons is this. It's called bounce. And so let me just show you. If you were to match, or if you were to measure the voltage across the Arduino pin, right? So it's nominally 5 volts here, and this is just very short. This is a 2.2 millisecond space from this point to this point. It's very, very short amount of time, and you were to push that button in, what you would see would go from +5 to 0 a bunch of times. Again, this is only a couple of milliseconds, so this is very quickly. This happens very quickly, but you can see it does go from a 1 to a 0, 1 to a 0 a bunch of times. So you have to be aware of that. A couple things you can do is, well, let's say we wanted to put a capacitor across this so that it discharges very slowly. Well, you could do that. So you could kind of put an RC network here, like we did before in our example. Or you can actually do this in software. I'll show you a trick how you can write some code that can kind of debounce or kind of debunk the debounce to make sure that it's a true 1 or a true 0. Because beware of switch bounds. So a couple of bits of homework. So I think I asked the class to, using this push button or contact closure input, essentially using this right here, this little schematic where you can detect whether this is connected to ground or not through a switch or a push button. Contact closure input. Come up with your own input sensor that could utilize this. And I think this is neat because you can actually do a lot with this, and it's very simple. This thing only takes a single resistor and some wire. So what can you all do with that? Well, I found this on the internet. This is pretty interesting. So here's a very simple vibration sensor. So you got a wire and this kind of resistor coming up through here and a coil of wire, and you can see if you were to shake this PCB, this coil of wire would go over and touch the wire of the resistor, making a contact closure. So just using this kind of simple bit of wire, you've made an actual vibration sensor. Very slick, very neat idea. And I think last Tuesday I came up with this. I was trying to think, well, what's another one? And this is kind of interesting. I didn't get a chance to finish this, but maybe you can get the idea. So you could use 3D printing with this as well, which is kind of what I was going for. So let's say you 3D printed this little plastic block, and there's a kind of a groove here, and two troughs, one in this direction and one in this direction. At the end of the troughs, I'm going to take this 22 gauge stainless steel wire, which I bought from Amazon. It actually already came in, so I'm going to actually make this sensor. And let's say I had one wire, two wires at the end, right? At the very end of each one. So one wire goes to ground, and the other wire goes to the input of Arduino. So one wire to ground here, one wire, and they're next to each other, let's say. And one goes to one pin of Arduino. Same thing, you have a ground wire here, another pin of the Arduino, same thing here, a ground wire, and one wire goes to another Arduino pin, and here, and this another. So we have 4 Arduino pins and 4 grounds at the very end. And I'm going to place one of these stainless steel or ball bearings in this tray, in this cavity. So what we have is a tilt sensor. So again, if the balls are right in the middle, you're fine. If this thing kind of rocks to this direction, the ball rolls in this direction and will make a contact. So I know that this thing's tilted in that direction. If this whole thing tilts in this direction, the ball will roll here, and these two contacts will close, and I'll know it's in this direction. And then in this direction, same kind of deal. Ball, if you tilt it in this direction, the ball rolls to here, making these two contacts close. If you go in the other direction, and the ball is touched in this direction. So I can detect if this thing is rotated, left or right, or forward and back. And then here's the really cool thing. You go, well, if I put that there, it's pretty much going to roll to one side or the other because this is flat. But you go, since I've 3D printed this, I can take this and tilt these up a little bit. So let's say, heck, I can even tilt them up by 45 degrees. And so that way, this thing's not going to actually go until the tilt goes by plus or minus 45 degrees on here. Or I can make it 10 degrees or whatever. So I can actually make a tilt sensor that only acts when this thing tilts at a certain angle in either direction, simply by using a couple ball bearings, a 3D printed piece, and some stainless steel wire. So that's kind of a neat. I'm going to build this thing up. I think it'll be kind of fun. But just shows you how you can make a tilt sensor using the contact closure input approach. Also, the second thing is to go through the Arduino website and learn as much as you can, because we're going to focus on how to program the Arduino to take inputs from things like this tilt sensor. That essentially ends our part 3 is of sensors in the Arduino. Next week we're going to go over programming the Arduino to actually interface to a tilt sensor or an LED, and it'll be a very introductory course to programming, but I think with a combination of what we go over in class and the Arduino website, you'll be off and running on your next project. Thanks a lot.